Welcome to the Chemistry 1A Pre-Lab Lecture Series. Today we'll be preparing to do Experiment 2, Mass and Volume Measurement. The learning objectives today are to learn the proper use of electronic balances and glassware, to determine which glassware is best suited to which task, and to learn to read and record accurate measurements with the correct units. Towards the end of the experiment, we will prepare a standard curve and also learn how to calculate percent error and standard deviation. The experimental objectives are twofold. In Part A, we will determine which glassware gives the most accurate and precise volume measurements by doing a series of experiments and comparing our data with the rest of the class. In Part B, you will determine the percent sodium chloride of an unknown solution of sodium chloride using its density, which you will determine experimentally. The hypothesis is there a correlation between the concentration of a salt solution and its density? When measuring mass or conducting any sort of scientific measurement, it's important to use the right tool. And so we want to make sure we're using the best scale for the job. In the Chemistry 1A laboratory, we have two types of scales available. We have the pan balance, pictured at the top, and the analytical balance, pictured at the bottom. And I'll explain how these work in a moment. It's important to always tare or zero a scale before using it to calibrate it to record no mass. It's also extremely important to record all of the digits that appear on the digital displays of these scales to ensure that we have the correct number of significant figures in our measurement. So a pan balance is one that you might be most familiar with. It resembles a scale that you might use in your kitchen or perhaps a bathroom scale. It's typically used for items that weigh between 0.1 and 100 grams. This is because it measures down to 0.01 decimal places. Whenever we are using a piece of equipment that gives us a digital display, the last digit displayed is considered uncertain, as it is an approximation of the lower decimal places. So if we had an object which weighed 0.10 grams, then we are confident that it's at least 0.1 grams, and the 0 is an approximation of the last digit. When we use a pan balance to weigh an item, we do not put the item directly on the scale, but rather use a weigh boat. This is a small plastic dish that weighs very little and can be used to hold our sample to keep the balance surface clean. So we'll place the weigh boat atop of the scale and press the 0 key to subtract the mass of the weigh boat from the measurement of our sample. We would then add our sample and record its mass in grams using all of the decimal places displayed. The analytical balance, on the other hand, is typically used for smaller samples that weigh between 0.001 and 10 grams. This is because an analytical balance will display a mass down to 0.0001 grams, or 1/10 of a milligram. You will note that an analytical balance has 3 sliding glass doors. These doors prevent any air currents or small drafts from causing a drift in the mass measurement. It's important that these doors are closed both when zeroing or taring the instrument and when weighing your sample. So when using an analytical balance, first place your weigh boat inside the weigh chamber, close all 3 doors, and press the tare button and wait for the instrument to display 0 in every decimal. Once the instrument is zeroed, open the door, add your sample to your weigh boat, close the door, and wait for the reading on the digital display to settle. Record the mass of your sample, including every decimal place displayed. An analytical balance will usually display the mass in grams, but can be adjusted to display the mass in milligrams or 1/1000ths of grams. Let's move on and discuss the different types of glassware that we will be using. There are 5 types of glassware that you will need to become familiar with for the Chem 1A laboratory. This includes the beaker, which you are probably already familiar with, the pipette, the burette, which you may have used before in your high school or other undergraduate chemistry classes, the graduated cylinder, another fairly common piece of equipment, and the volumetric flask. The volumetric flask is a large vessel with a narrow neck and a single calibration line. This allows the flask to hold a large volume of liquid, but to measure that volume extremely accurately. To fill a volumetric flask, first add solution to fill into the large reservoir portion of the flask. Then add drop by drop until the level of solution rises up until you can see that the curve of the solution against the glass forms a meniscus, and that the very bottom of this curve or meniscus touches the etched line. Last, it is important to note that a volumetric flask is calibrated to contain an exact amount of fluid rather than to be able to pour out that amount of fluid. The graduated cylinder is another very accurate piece of glassware. It is a long, narrow tube with an opening at only one end, and it has numerous gradations marked along the side of it. These gradations are calibrated to contain, just like the volumetric flask, so the graduated cylinder can be used to very accurately measure an amount of solution, regardless of whether it matches a specific calibration point, as for the volumetric flask. The burette is another long, narrow tube of glass. However, this one is open at both the top and the bottom, though the bottom entry can be blocked by the use of a stopcock. The burette is also having very many marked gradations down its length, and so it can very accurately measure a volume that is dispensed. The burette is designed to dispense an amount of liquid with high accuracy. By noting the volume on the gradations of the burette before and after delivering some sample, we can take the difference of the volume measurement before and after and calculate the amount that was delivered. Therefore, it makes sense that a burette is calibrated to deliver. The pipette is similar to the burette, being a long, narrow tube with many gradations open at both ends. However, it does not have a stopcock to prevent flow. Instead, a pipette is used with a rubber bulb, which will provide suction to suck up solution into the pipette so that it can be transferred into a new vessel. Therefore, a pipette is calibrated to deliver. Lastly, the beaker is a large, wide-mouthed vessel that has very few gradations that are marked with fairly low precision. A beaker should only really be used for rough volume measurements and to prepare large amounts of solution. It is suitable for containing solutions that will be transferred or for mixing solutions. Now that we're familiar with the balances and glassware that can be used for determining mass and volume, we can discuss the calculation of density, which is defined as the mass per unit volume of a substance under specified conditions. The equation for density is thus lowercase delta for density equals m for mass divided by v for volume. Given this equation, it's fairly clear that the units are going to be mass units over volume units, so density is usually recorded in terms of grams per milliliter or grams per centimeter cubed. It's interesting to note that this use of units is directly related to water. For 1 milliliter of water is equal to 1 gram of water. Likewise, 1 cubic centimeter of water weighs 1 gram. The density of water at room temperature is approximately 1 gram per milliliter. However, I noted at the beginning of this slide that density is the mass per unit volume of a substance under specified conditions. The density of water will change with temperature. It's important to note the temperature of the water you're using for this experiment before calculating your densities. So if the objective of this lab is to measure the density of a solution based on its mass and its volume, which glassware should you choose to get the best volume measurement? Which balance should you choose? You will determine the answer to these questions in part 1 of the experiment. You will be divided into groups, and each group will be assigned one piece of glassware to use in measuring the density of water. As I said earlier, the density of water is about 1 gram per milliliter. In fact, it is exactly 1 gram per milliliter at 4 degrees Celsius. At other temperatures, water becomes less dense. Therefore, we will report the density of water at the temperature that we actually have. Your task will be to devise a method that will use the glassware you were assigned to measure a volume of water and to weigh it, and perform this process 3 times. You will record the volume as you measured it from the gradations on your glassware. Next, you will use the mass of the water and the known density to calculate the true volume of that water at the current room temperature. By comparing your measured volume to this true volume, you will have an idea of the accuracy and precision of the glassware you chose. We will then compare your accuracy, as defined by percent error, and your precision, as defined by standard deviation, to the class and compare the class data to determine which would be the best glassware to carry through to Part 2. To calculate accuracy in terms of percent error, we first need to calculate absolute error. Absolute error is defined by the difference between your experimental reading and the true value. In this case, you would take your measured value from the glassware and subtract the true volume of water that you calculated from its mass and the known density. We would then, for percent error, or for accuracy, divide that absolute error by the true value and multiply it by 100%. You will see that depending on whether your experimental value is higher or lower than the true value, you will have either a positive or a negative percent error. Precision is calculated as standard deviation, and it is described by this large formula here, which you will be asked to learn throughout the course and apply. Standard deviation, or S, is equal to the square root of the sum of each value minus the average value squared divided by the number of values minus 1. We will go over this calculation in more detail in Study Guide A. In Part 2, we will determine the density of known salt solutions and use the density of those known salt solutions and the density of our unknown salt solution to find the concentration of salt in our unknown. This is done using a standard curve. Standard curves are a common tool that are used to find the relationship between two variables. For instance, in this experiment, we will be looking at the variable percent sodium chloride and the variable density. The fixed variable, so in this case percent salt, will be plotted on the x-axis, the horizontal axis referred to as the abscissa. Values that come from our measurements are dependent values, as they depend on the fixed value on the abscissa, and these values are plotted on the y-axis, or ordinate. By plotting the data points at the x and y ordinals, we can see a trend appear between the different data points. We then draw a straight line through the data points so that it touches as many points as possible to reveal the trend. This way, if we have one variable that is known, we can use our standard curve to predict the second variable. So for today's experiment, you will determine the volume and mass of a set of sodium chloride solutions and use those volume and mass measurements to determine the density. You can then plot the density and the percent sodium chloride onto a graph with percent sodium chloride on the abscissa and density on the ordinate. From the density of your unknown, find the percent sodium chloride using your graph and standard curve. You would take the known density, travel along the graph until it hits the trend line, then travel downwards to the x-axis, or abscissa, to determine the percent sodium chloride. To ensure that you're getting the best trend line that fits through your data points, and to increase the opportunity for high accuracy in your calculations, it's best to use a spreadsheet program such as Microsoft Excel to prepare your standard curve. I will now go through how to prepare a standard curve using Microsoft Excel. I currently use the Macintosh version of this software. However, all versions of Excel are very similar, and these instructions should guide you how to use Excel on any of its incarnations. When you open Excel, you should see the spreadsheet arranged into columns headed by letters and rows indicated by numbers. Begin by entering your variables into two columns on the spreadsheet. I'll first put my fixed variable into column A, and it's always a good idea to label your columns so you can understand your spreadsheet when you look at it later. And I'll put my dependent variables, my density in grams per milliliter, into column B. Okay, so you'll be given 0%, 6, 12, 18, and 24% sodium chloride. And just for practice sake, I'll make up some densities that you might get and enter them under my density column. Okay, now that I've entered my data, I want to prepare a standard curve. Remember, with your data, you're going to have more than one measurement for each % sodium chloride sample, and so you can just enter those again below, like 0 again, 6 again, etc. And I'll just omit those for now. Okay, so to make the standard curve in Excel, begin by moving your cursor to the upper leftmost data point, and then click and drag down the column and across to the next one so that you've highlighted all of your data. There are many ways of creating the chart using the different Excel platforms, but I'll use the one that's the most common between all of them in my demonstration. So I'll go to the top of the screen where you see Insert, click on Insert, and then choose Chart. You'll see that on my screen a number of chart options have popped up. This may come in a separate dialog box in your version of Excel, but the point is the same, that we would choose from all of these graph types a scatter plot. Scatter plots are graphs where you simply get a point added at each of your data points. Choose the one that does not have any lines going through it, as these lines are not true trend lines, but rather connect the dot type lines. So we'll choose simply the marked scatter plot. The graph appears in its most simplest form, but we want to have a fully labeled nice graph. And so by choosing chart layout, we can add a title and axes titles to our graph. So I'm going to first add my horizontal axis title, and that's going to be my % sodium chloride. And there we have a title. I'll then add a vertical axis title, and that will be density in grams per milliliter. Since I only have one set of data, I do not need to indicate which series this is, so I'll delete that to make more space. Alright, our graph looks a little better, but just to make it easier for you to see, I'm going to move it into its own screen. And so to do that, if I had a mouse, I would use my right-click button, but since I'm a Mac user, I'm just going to use Control-click. And you see a variety of options here. If you click on Move Chart, you can put it in its own sheet. So New Sheet, Chart 1, OK. All right, now everything is nice and big and clear for you to see. So the next step is to add a best fit line through our data points. And on Excel, a best fit line is called the trend line. To add a trend line, move your mouse until it is hovering over one of your data points. Again, right-click or hold down Control and click, and go to Add Trend Line. We expect that the density of the solution will increase linearly with % sodium chloride. And in fact, our data points look roughly linear, so we will choose a trend line that is linear, as is the default. You should see somewhere in your dialog box an Options tab. And under Options, we can select Display Equation on Chart so that the equation of our trend line will be clearly displayed, and we can use that to determine the concentration of sodium chloride in our unknown. Click OK. And we can click and move our equation into an area where it's easier to see. There we go. So our equation is written in terms of x and y. You'll remember that the x-axis is the horizontal axis across the bottom, and that the y-axis is the vertical axis. So what this equation is saying is that density on the y-axis is equal to 0.0115 times the concentration of sodium chloride in percent plus 1.082. We can rearrange this equation by subtracting 1.082 from density and then dividing that value by 0.015 as follows. So if we have density minus 1.082, take that value, that's equal to 0.0115 times the concentration of sodium chloride. Note that I'm using these square brackets to indicate concentration. Okay, one last step. If we divide both sides by 0.0015, we'll be left with our concentration of sodium chloride. So concentration of sodium chloride is equal to density minus 1.082, all divided by 0.0115. So if I put in my density of my unknown sodium chloride that I determined by my experiment, by taking its weight and its volume, then subtract 1.082 and divide that subtraction by 0.0115, I will know my sodium chloride concentration in percent. And that will conclude the objective 2 of experiment 2, which was to determine the percent sodium chloride in an unknown solution. Okay, a couple of technical tips for you. After part 1, we will discuss as a class the best glassware to use. We will choose the glassware that gave the most accurate and precise volume measurement. When you are doing part 1, note that the volume that you use for each measurement does not need to be the same, so long as you're accurately recording the volume each time and also recording the mass. Throughout both part 1 and part 2, it's important to record all the volumes in milliliters and all the masses in grams to as many significant figures as possible. This means do not overlook any digits displayed on the balances, record them all. And when using glassware, try to make a guess between the gradations that are on the piece of glassware as to what the next fraction would be, and report that digit as your final significant figure. Remember, because you're taking the volume as the glassware gives it to you and then weighing the solution, it's important not to have any of the solution on the outside of your glassware. So take a Kim wipe or a paper towel and wipe off any droplets that are on the outside of your glassware. This video should have helped you to prepare for experiment 2, mass and volume measurements. However, don't forget to also read your lab manual for more detailed information. Your pre-lab will be due at the start of class, and you'll need your goggles and lab coats for this one. Have fun! Bye-bye.